Hey guys! Alright, today we're going to do Chapter 8, Section 4, which is on geometric series. So we've already talked about arithmetic series, and remember that in an arithmetic series we're adding all the terms together, and each of our terms has a constant difference, meaning that I'm adding or subtracting in order to get to my next term. In a geometric series, I'm multiplying or dividing to get to my next term, which is why we call it geometric rather than arithmetic. So remember that a geometric series has a common ratio, meaning that you're multiplying by some number each time. The sum of a finite geometric series, S sub n equals g sub 1 plus g sub 2 plus g sub 3, all the way up to g sub n, with first term g sub 1 and constant ratio r not equal to 1, is given by this formula here. And again, this can be found on your formula sheet, so make sure you know where it's at. So S sub n, the sum of my nth terms, is equal to my first term times 1 minus my ratio to the nth power divided by 1 minus my ratio. So, whenever I have a finite geometric series, meaning that I'm not adding up an infinite number, okay, I'm just adding up a certain number of terms, I can use this formula here in order to solve for that sum. So, this problem here, it's asking me for the sum from terms 1 to 7 of this series here. Notice that this is in my geometric explicit formula, so I've got 18 times 1 over 3 to the I minus 1. So, if I were to talk about my first term of this, my first term is 18, so that's my g sub 1. My r value is 1/3, okay? And my n value in this case, it's asking me to sum from 1 to 7, so my n value is going to be 7. So if I plug that into this formula here, I have s sub 7 equals, my g sub 1 is 18, 1 minus 1/3 to the 7th over 1 minus 1/3. So, plugging that into my calculator, if I do 1/3 to the 7th power, I do 1 minus that answer, take that number times 18, and then I divide that by 1 minus 1/3, which is 2/3. I'll end up getting 26.987, which means that the sum of these terms is approximately 27. So, once you add all those up, you will get approximately 27. When you think back to our limits, remember that a sequence is convergent when its end behavior approaches a finite number. So again, we're thinking about, as those x values are approaching infinity, what's happening to our function, what's happening to our y values. So a sequence is divergent when its end behavior approaches an infinite number, which is either infinity or negative infinity. So if I look at these two graphs here, this graph is an example of a convergent sequence because I'm getting closer and closer to 0, whereas this graph right here is an example of a divergent sequence because as my x values are getting larger, my y values are approaching infinity. So what we can say is that if our constant ratio is less than 1, meaning that it is somewhere between 0 and 1, it's a fraction of some sort, I know that my series is going to converge. If the absolute value of r is greater than or equal to 1, then I know that the series is going to diverge because it's going to continue to get bigger and bigger, or it's going to continue to get more and more negative. So this makes sense because if I'm multiplying by a number greater than 1 each time, my function is going to continue to increase. If I'm multiplying by a fraction each time, my number is going to continue to decrease. But if I'm dividing by the same number every time, I'm never going to get to 0, right? I'm never going to get to a negative number. I'm never going to get past 0 because I'm just going to split that number into smaller and smaller increments. So the second question is problem number 1, convergent or divergent. So let's go back up here. For this problem, our r value was 1/3. I know that 1/3 is a fraction between 0 and 1. Therefore, I would say that that problem was convergent. Alright, that is everything for section 4.